change it to, you know how to change the pointer?
Yes.
Okay, so hello everyone. My name is Roy Cohen. I'm a PhD student at the physics department. And I think I'm doing something different than what most of you will do. I wanted to choose something that related to my field, that I will be able to talk more with more knowledge and to able to tell you more details. So I've chosen a good story. It's not really a misconduct of an experiment.
Hopefully it's proper conduct because it's yours, right?
Yeah, it's not. Yeah. There are people that maybe did a misconduct, but the physics community still hasn't said it's a misconduct or a fraud. And those group of people showed maybe that a lot of people are wrong in the community. And they really tried to show, and with a really good paper, to say why everyone else is wrong. So we can start with a bit of a background. Resistivity is
feature.
It's a feature of materials, property of materials, and we can divide each materials to different types of resistivity, which is its resistivity. The main three types are the insulator type. As you can see, we have a graph of temperature as a function of resistance, and an insulator, its resistance will increase as you decrease the temperature of the material, and at the end, it will go to infinity at 0 temperature. The other types are metal, which have a finite resistivity when you reach 0 temperature, which means it conducts electricity. We're using it in our days everywhere. And the third type is a superconductor, which was discovered in 1911 on mercury and then on many other materials, which in a specific temperature, which is called a critical temperature, the resistance suddenly drops to 0 and it conducts perfectly. It doesn't have a resistance. And this superconductivity, actually, I guess most of you know, I researched a lot those days, even those days. But all those three types are applied only for 3D systems. The metal, the insulator, and the superconductivity can be observed at 3-dimensional systems. What happened in the 2-dimensional systems when the samples are too thin? Theorists shows that in 2-dimensional systems, you can't have metallic state. You can have superconductivity. It's very unique. You can have insulator behavior, but you can't have a metallic state in 2-dimensional systems. Is that so? Let's see.
But does that mean that if you cannot have metallic states, you cannot have superconductivity in 2D?
No, you can have superconductivity.
You can have to, but you cannot have metal. So you can have semi-metal, but you cannot have metal.
Yeah.
But superconductivity can occur.
Can be occur. Yeah, it's because it's still needs a lot of explanation, but superconductivity has much more than just 3 electrons. So it's a bit more complex why superconductivity can be happening in 2D materials, but not a conventional metallic state. But there is a phenomenon called superconductor-resonant transition. It's a quantum phase transition. That means we have a non-thermal tuning parameter. I won't go too much into explanation on this phenomenon, but as you can see, one sample in this case it's an indium oxide sample, can undergo the transition between a superconducting state, its resistivity goes to 0, to an insulating state. On the other side, when you just change a parameter.
What is the parameter?
Right here, it's a disorder of the sample, but you have many types of tuning parameters for this phenomena. It can be magnetic field, it can be gate voltage, compounds of the material, the precision of the compound, etc. And although this phenomenon was investigated a lot since the year 2000, there are still a lot of open questions on this phenomenon, and one of them is what exactly happening in the middle. Is this in transition from a superconducting to an insulator directly, or it's going to the metallic states in the middle? Something that I forgot to tell you. All of those, this phenomena occurs at two-dimensional systems. So all these experiments.
These are experiments or theory?
Experiments. This is an experiment done here in Bar-Ilan.
So what are we measuring? What is a 2D system and what are we seeing here?
It's a two-dimensional indium oxide. It's a thin layer of indium oxide sample.
What is thin? It's atomic level?
No.
No.
Two-dimensional in superconductivity, it means that the dimension is lower than the correlation length of the superconductor. So right here, it's a 13 nanometer thickness of sample.
Okay, deposited in an evaporator.
Evaporator on some
and this is one sample that you are tuning the disorder. How do you tune the disorder?
With annealing. You're heating up the sample, and you can.
So you start with fully disordered layer. You do the resistance, and then you take it out of your cryostat. You anneal it. You do it again and again. And that's experiment. Okay.
Yes, this is experiment. Yeah. It takes time. You cool down the samples to cold temperature. You can see 1 Kelvin, almost the 0 temperature. And each time you heat it up, anneal it, and go back again. And you can see that you start with a very disordered sample, and when you anneal it, it becomes superconducting.
But is there any surprise here? I mean, I could imagine when you have a very disordered system that it will never go to superconductivity.
Yeah, the surprise is it's still not here. Superconductor and sort of transition have explanation why it occurs. The big surprise happens in a lot of experiments in the middle. When people started to see a saturation in the resistance, as you can see here, we have 1 over T.
So definitely, this is not your work, this is somebody else's work.
Somebody else's work.
What is the system? What are they looking at?
I'm not sure which materials they are using, because there are a lot of different types.
Mm-hmm. But again, it's some deposited layer, thin enough.
Yeah.
And what is the parameter that's changing here?
It's a magnetic field.
Magnetic field. Okay.
Yeah, you can see here it's from 0.05 Tesla to 9 Tesla. You can see its resistance in a log scale and 1 over T, which means the right side is the lower temperature. And we can see here a saturation in the resistance.
Which resembles metallic behavior.
It resembles metallic behavior, that's right. And it's not just this experiments. There is tons of other experiments that shows that inside the superconductor sort of transition, although we have two-dimensional systems, we can observe the metallic states. They call it anomalous metal. They call it Bose metal. It was maybe a huge discovery for the physics community. It's against all the theories that said that you can't observe a two-dimensional metallic state. And a lot of people try to understand how it's happening and show that it can happen in more and more systems. But then comes 2019, a huge group of people. One of them is Tamir, that said to the whole community, hold your horses, you're maybe doing it too fast and maybe wrong. The result of sensitivity in the measuring of these thin layers, and they address in their paper 8 or 7 other papers that shows this metallic state in two-dimensional systems, and they said them, you are maybe doing it wrong. It's not an anomalous metal, it's still a superconducting state, and the difference is you just measure it wrong. You need to add filters to your systems, and they show here in their graphs. They do it on 2 different samples. On the one hand, they have an anomalous indium oxide, something that it's not in order. On the other hand, then they have niobium selenite, which is crystalline 2D superconductor. And they showed that they measured them 2 times. The first time without any filter.
What do you mean filter?
They used a low pass filter, which
so you're talking about the electronics, the measurement device. So what do you use usually to measure this? It
depends on people, but usually you pass a current.
Is it AC or DC?
DC? It depends on the group. Most of the people pass both of them to see if there is an impact of the AC or the DC.
But when you're talking about filter, I think AC. So
yeah, most of us using AC because it's more accurate.
So you have a function generator and a voltmeter, basically.
Yeah,
okay,
that's all.
All right. So you need to add a filter, a low pass filter. So there are some high frequency issues coming. Okay, tell us.
And they just showed it. It's still unknown what's the high frequency.
But what is the filter they are using here?
It's a low pass filter. If I remember correctly, any other than 10
it's an RC.
Kilohertz, just an RC, regular RC.
To pass kilohertz and below.
Yeah, nothing.
Nothing fancy.
Nothing fancy.
Okay.
Nothing fancy.
Wow.
And as you can see, the differences between an unfiltered, the red one, where you see the saturated in the resistance, and on the other hand, you can see superconducting, which is filtered.
Did they use spectrum analyzer to look at the high frequencies?
They didn't show this on their sample.
But the first thing you want to do is to go and look at the high frequency, see what's there.
It's harder to...
What is the origin of this?
It's harder to see high frequencies because most of the noises are inside the high frequency. Mm-hmm. So start to get to the point when you don't know what is noise, what it's not, how you generate the frequency high enough without any noises. So here they just showed that in filtered sample.
Okay, so all the report on metallic states may be just artifact of the measurement itself.
Yeah. So they showed us the importance of a good and clean measurement. And although this paper is well known in solid states, in superconducting physicists, still there are guys that said, no, we did put filters on our samples, our anomalous metal is real, and it's still under debate, still not a misconduct of anyone. A lot of people try to convince each other which one are correct, and still theorists try to understand what is the origin of everything, so we can be...
People reported superconductivity also on misoriented graphene layers and so on, right? Which is way thinner than this.
Yeah, way thinner. Superconductivity can cause it.
With graphene, you start with semi-metal, right?
Yeah.
So it cannot be metal, it's semi-metal, but there are reports. So people have tried to do filtering on that data as well?
Yeah.
And?
In graphene case, they have a theories that back it up. Why the superconductivity can occur in twisted bilayer of graphene. This phenomena is very unique and very interesting. it's called Moire topology. It's not just graphene, there are a lot of materials that
it's a Moire interference, right?
Yeah, just twist two layers and the electronic properties, it's very
okay, but different. It's very different than this. This is isotropic thin material.
Yeah. So it's still under debate. And one more thing that I really loved about this paper, they really try not just...
So no retractions yet.
Not yet. Just people are published less quickly. Those stuff, if between 2015, when the anomalous metal starts to show up, to 2019, there were tons of papers about this. From 2019, it's way slower. In my group, we're waiting to show anything that look like. We are afraid to maybe someone will see this thing in our data. So it's still not understood and under huge debate. And another thing that I really like about this paper is that not just they try to convince you with nice graphs, they give you a lot of information in their paper. They have a paragraph, a big paragraph on the materials and method inside the paper itself. And even more, if you want, they address you to a different PDF, which is supplementary materials. And in this one, they showed how the system looked like, explanation of how they measured, a specific of any of their materials that they measured. I never saw it on any other papers. So anyone even asked can look what they did and do exactly the same as they did. Sorry. And it's still not publishing the raw data as we speak. And it's the first lesson, but I think it's the right direction to publish almost everything you have on your experiment.
Especially if you have controversial results.
Yep. Especially if you have something that it's unknown and under debate. So you can, I think most of the physics community will love to see everything you have to show, and the people who are related to this work. Even
but you think the raw data of the IV, whatever measurements, is not available?
No, not yet. I think if you will ask them, they will give it to you. But
I have to say, in my field already, it's kind of almost standard. Everybody deposited raw data in depositories.
I hope this
actually, it's interesting for me because physicists were the first to use archives and put preference out there. I would expect them to be the first to put raw data as well.
Somebody didn't look good enough to see if there is, but I didn't saw raw data in papers yet. But I did saw less information than what they gave. And it's really nice to see people that gave a lot of information of how they did it and what they did it, what is the sizes, everything. It's not something that I used to see.
Good. That's your last slide.
Yeah. Thank you very much.
So this was not yet a misconduct or wrong work, but I think the controversy is interesting, and you have to be very careful when there is a controversy.
Is anyone questioning the relevance of the filter, applying the filters?
Well, I don't know enough about the field. Maybe you can explain to us, but I guess superconductivity is a DC phenomenon. So maybe there is a justification just to eliminate noise, you put a low-pass filter. But in the past, people did not put that filter in measurements.
Right.
And for some reason, only for these thin layer materials, the filter is important. But if you do bulk 3D, it's not important.
When you're
so you need to justify why you are adding a filter, and you did not need the filter before.
The sensitivity of dimensional systems are...
You don't have a signal, basically, because it's very thin.
A lot of things, the resistance on the...
So those measurements are much more difficult because you have...
To measure an insulator, it's very difficult in a lab.
Because the resistance, I guess, is extremely high.
Yeah. As you go thinner and thinner, it's harder to pass current because you can burn the sample, you can change everything. So even small noise can change everything in your measurement.
Okay. This 2D behavior applies to any metal?
It's just the superconducting. Yeah, the anomalous metal occurs in the
only materials that exceed
superconductivity, and then you can destroy the superconductivity slowly enough to see the anomalous metals in the middle.
Mentioned from 2015 to 2019, there were tons of paper. So after 2019, nobody has...
No, there is still people that said that they observed it, people that are...
No, but this is
the response of the people who said that, well, you can use the filter and can come out with no result. It's like...
Well, this is actually a very good example that the scientific community was able to pick on this very quickly. Think about the story of cold fusion in the 90s. Okay. But here there is an interesting observation, and in 4 years after the observation, people will say, hey, wait a minute, maybe the measurements are not done correctly. That's actually very fast time constants for this type of things. It's not that bad.
And all of the physicists in this field still trying to understand if the filters are really necessary, if what they are really doing, why we are seeing the anomalous metals in noisy samples, why the filters are good, what is the differences. There is a lot of theories that try to really understand what the behavior of the group.
So that's your PhD, that you're going to give an answer, right?
Not exactly.
Okay.
I'm approaching this phenomenon in a different way.
You're Aviad?
Yeah.
Any questions online? Go ahead.
Yes. Can I have again, so you've mentioned that once there was one publication about these anomalous metals, a lot of publications came after it, right? Yeah. Until this paper in 2019. So it's an interesting psychological issue because once a lot of people measure those materials, and once someone sees a paper that states something like anomalous metals, and then you measure the same thing, maybe because you didn't use a filter, or maybe because it's actually a real effect, but you will be more prompt to publish your results because someone else already saw a similar thing. So this is I think it's also an interesting issue in this.
Yeah, I think so as well. After the first one, it was easier to publish this phenomena. The anomalous metal, it's real because already someone showed it and I'm not the only one.
Right. I mean, there is the herd phenomena, right? Effect Edel. Once, it's sexy, it sounds good, so immediately many people jump in and report the same. So all of this, I mean, today's 2 lectures, I really enjoyed them very much because they were exactly on topic, right? I mean, how do we do science better? Everywhere you go, you'll find that it's so easy to make mistakes, and you have to be very careful. You have to trust your students and colleagues, and you have to, on the other hand, make sure that you check them as well. It's very easy to have the wrong hypothesis, the wrong concept, and you're so convinced that you're right, and you're pushing and you're publishing, and other people immediately jump and say, we saw the same. And so I don't have answers, but I want to introduce those questions and dilemmas and difficulties. More from people at home? Comments? Just turn on your mic. So for the students' presentation part, we will do that. After each presentation, we'll open the forum for discussions. We all try to learn from all the different cases that will be presented. Again, I encourage you to fill in the open slots for next week. So people can change their dates based on the Google Sheets. Any other questions, requests?
Actually, I have a small question. You presented this case as a possible misconduct, but is it? It
no.
Sounds more like a problem that
I did not.
Someone picked on.
Why do you say that?
No, you mentioned a few times possible misconduct and
it's still under real debate.
Well, no, but there is no evidence for misconduct. It's just
not yet.
Wrong interpretation.
Or methodology.
Yeah. Well, now there is a question: do you need a filter or not?
Yeah.
But the initial experiments and the additional reports were maybe wrong interpretation because the measurements was not done correctly. But this is still out, you know, for the jury to decide. It's not a done deal. But there is no evidence for anybody faking data, right? Yeah. Okay, well, thank you very much. Again, I would encourage people to come because it's nice to see you all. At least for next week. And by the way, we can continue in this format while I'm in LA. You guys can be around this table and I'll be on the screen. That's fine with me. I know it's hard, it's 7 p.m., but whatever works. Okay, well, thank you, everybody. Thank you for guys at home. See you next week.
Thank you.
Bye-bye.
Thank you very much. Bye-bye.
Bye.